regression, whatever regression tool you're using, its goal is to minimize those squared errors. That's why they call it the least squares line. Okay, minimize those squared errors. In other words, fit this data as best as you possibly can. This is linear regression. Okay, it will always be fitting a straight line. It's linear regression, and linear is y equals, a plus b x. Okay, that is going to be the equation of this line. Then describes this relationship between these two, and then also can be used for predicting. Because if you know the slope and the intercept, you can plug in an x number of times playing the game and predict what y would be, right? That's what a regression equation is for. It comes from the regression line, which has been fitted to your data. The best possible fit it can be to this data. That's the line, that's the equation, that's what we use it for, equation of that line. Okay. So it looks like, and this is what someone would do that was really doing research, that there's very definitely, with a correlation of 0.855, very definitely a reason that we should pursue this regression, to say, yeah, this is probably a model that we can very much use X to help us explain and predict Y. Okay, so we go ahead and do the regression now that we believe that it's worthwhile doing. Okay, so I'm going into regression classification, drop down, and I'm choosing regression, just plain regression. All right, a couple of things. I know I've referred to this as simple regression, and I know up here it says this multiple regression. Leave it on multiple regression. Multiple regression is regression where you use X or X's to help you predict and explain Y. Okay. Simple regression is just a specialized subset of that where you only use one X. That's all. So it still is what we refer to as a big picture multiple regression, but it's a subset of that where you just have one X. That's why we call it simple regression. Okay, so leave that alone. That will come up like that, leave it alone. Then we've got these tabs of things. First tab where it says variables. Absolute first thing you need to check is, are we on the right data set? Okay, first thing you need to check. Okay, because it may not come up, trust me, you may not come up on the right data set if you had more than one. I know we don't have more than one right now, but it may not. Video regression. Then in regression, we refer to X and Y as the independent and the dependent variable. X, the independent variable we think moves independently, and Y, which we think in some way depends on X. Okay? So the independent variable X, okay, independent X, is the number of times playing. The dependent, or Y, is the game score, just like it, but that's independent and dependent now. Okay, on this tab, I have made sure I'm on the right set, and I've checked my independent, dependent variables appropriately. Next tab, parameters. Don't do anything here and never go to this tab again. Okay? We are not changing any parameters, and you never need to look at this tab again. Okay? Next tab, graphs. If I ask you for a graph, if the problem asks you for a graph, add them. If it doesn't, don't. Okay? So now I'm going to put a couple of them on here that I want to show you, but I'm just want to put that information out there for you. So I'm going to do the fitted values versus the actual, and I'm going to do the residuals versus the fitted. The first one in the list, the third one in the list. I'm going to do those because I want to talk about those. Okay. Okay. Done here. Next tab, options. Go ahead and say display the regression equation. Might as well. Be easier to look at if it's already displayed, and then I don't have to write these really long things on the board. Okay. So display the regression equation. But now I will tell you, after this time through, we'll often do predictions and regressions at the same time. But this time through, I want to do it in steps. Okay. So unclick this where it says include a prediction set. We haven't set one up. I don't want to do one yet. We'll come back to this in just a few minutes. Okay. So do your regression equation. Don't do a prediction set. I have looked at each tab, and I've made sure they're right. And now I click OK. Takes a minute. Okay. Here's my regression output. Before I show all of that, I want you to see this correlation, 0.855. That is, in my regression output, called multiple R. Okay, and here's what multiple R is. Okay, that 0.855. Multiple R, we get, correlation, we get from plotting our actual Y, what happened, against our fitted or predicted, you can call it either one, Y. Okay? All right, so here, let's say your Y value was 1, and you predicted it would be 1. That'd be awesome. 1, 1. Okay. Let's say your actual Y was 2, and you predicted it would be 2. You see where I'm going with this? Your actual Y was 3, and you predicted it would be 3, and then 4, and then 5. In other words, you had perfect prediction. You had perfect predictions for your Y's, you know, like it was exactly the same. You know what that would produce? A straight line at a 45-degree angle with a slope of 1. A correlation of 1. A perfect correlation. Okay, that would be a perfect correlation. Now, if something is inversely related, your correlation could be exactly perfectly -1, okay? Where you predict something. Anyway, so your correlation, the closer it is to either -1 or 1, the better it is, okay? Those are great correlation. The closer it is to 0, the worse it is. In fact, there's no correlation if it's 0. There's no correlation between these two things. We can tell that again from the plot that there was a correlation between these, and in fact, it was pretty good. It was 0.855, moving up closer, you know, to 1. Okay, there is our plot of our game score against our fitted game score. And so it did have a pretty good, you know, maybe not a perfect 1 slope, but a 0.855, you know, pretty good slope there. That's where that 0.855 comes from. Okay. However, when people try to describe what that means, it doesn't make a lot of sense to other people to say something like, well, it's the slope of the line when you plot the Y value versus the fitted Y, you know, it's like, okay, what does that mean? And so instead of talking that much, I mean, we know correlation should be high, and we know that would be good, that higher and better and closer to 1 or -1 than it is. But what we use instead is something called R squared. We square that value and come up with R squared. And there's a reason that we square that value and come up with R squared, and that's because R squared has a much more definable, interpretable meaning, okay? What it means is R squared tells us the percent of the variation in Y that can be accounted for by X, okay? In our model, the percentage of the variation in the game score that can be accounted for, explained by, okay, how many times you played the game. So specifically for our model, we can explain 73%, that 0.731, okay, we can explain 73% of the variation in your game score by knowing how many times you played, okay, or this person. Okay, so that's the 73%. That's what the point. It's much more meaningful explanation. That's why we use R squareds, okay, because they have that. So that's just the correlation multiple R squared, okay, and that R squared is this percentage. So in ours, the 73% of the game score can be explained by how many times the person's played the game. There's still 27% we're not explaining, right? And there's still 27% we don't know what affected it. The person's just really good, very skilled, very got really lucky that day, was highly distracted that day, you know, all the things that would cause it to be up, down, different from, you know, exactly. So there's there's certainly stuff that we don't know, but we didn't model any of that stuff we don't know, so we don't even know what else to put in there. We could begin adding things to it, but at this point, we do know that 73% of the game score can be explained and predicted by too, actually, the number of times somebody has played. Okay. there's this number, the standard error of the estimate, which works a lot like a standard deviation. If you remember standard deviation from statistics, you have these curves where a standard deviation that's very small would produce a curve that's much more tight, and a standard deviation that's large would have to be a much wider, more sprawling, kind of curve. Okay. That's because the standard deviation measure is telling you that 2/3 of your data falls within one standard deviation either side of your mean, right? Okay, that's what it's telling you. It's telling you that 95% of your data falls within 2 standard deviations either side of your mean. And we use that 95% interval a lot. It's a real conventional interval to use. Roughly 2/3 of your data falls within. So this standard error of the estimate acts a lot like standard deviation. And just remember this number, and we'll come back to it later, but it's roughly 12,000. Okay, it's pretty close to 12,000. Okay. All right, we're going to use that in a few minutes when we do a prediction thing, but we'll come back. We're going to skip the ANOVA table and not talk about it, but we are going to look at these coefficients. And I really don't want to look at those coefficients without also looking at their p-values. Like I know in this model these p-values are all going to be fine because we only have one x variable and it does a great job of predicting, explaining our y. 73% is pretty good r squared, okay? But before we really even want to talk about our coefficients, we really should look at p-values, because if we ever see a p-value here that's greater than 0.05, what it means is that x, for instance, we don't have multiple x's here, but when we do, that x is not statistically significant in our model. If it's not statistically significant in our model, it's not helping us to explain why. Okay, it's just not statistically significant. That is not the case here. Our p-values are great. They're all really small, so we're good. So now we look at this and say, well, how would we explain those two coefficients? Well, it might help if we put those two coefficients into an equation. Okay. Let me move off of it because it's making it look weird. Okay. The constant coefficient right here, our game score is equal to that constant coefficient, 11,735, plus coefficient for the number of times you played, so the 1119 times the number of times you played. Y equals A plus B times X. I mean, I guess what's it could be a B times X or either way. Y equals A plus B times X. Okay. That's our equation that came from this regression, which came from fitting the lines, this little, that line, the equation for that line, and these are the coefficients, plugged them right in here into the equation. But I don't just want to be able to look at this equation and go, oh, that's nice. I want to be able to look at those numbers and explain them, interpret them. That's a better word to use, interpret them. What is that 11,735 telling me in the context of this video game example? Which in the context of this video example is what?
The score somebody gets when they have never played the game.
Right. So it's basically like this base starting score that you would expect somebody to start at. You really have to loosely define this, and here's why. Because it's what it's technically saying is that the number of times you play to 0, okay, multiply this would be gone. This would be your score. Well, you wouldn't have a score if you played 0 times. So we have to loosely interpret this as this is kind of a starting score. Okay, that's pretty much where you start when you really have never played the game before. You probably start about here. Okay. On the other hand, what does the 1119 tell us? What does that number say?
For every unit increase in the number of times playing a video game, the Y increases by 1.
Yes, you expect for each additional time you play this video game that your score would go up in 1119, or an average would go up 1119. We know it's not an exact thing, but that's our expectation, is for each additional time we play the game that our score would go up 1119. You need to be able to interpret those values within the context of your problem. Okay, they need to be able to make sense like that to you. Okay, questions about these regression results? Because we've got another thing we need to do.